Yep.
Okay. I'm Tami Spector, as Piero said, and
Can you put the microphone closer?
higher. Okay. I feel like I'm loud. Okay. And I'm an organic chemist, so I teach organic chemistry mostly, at various levels, college and grad level. And as Piero said, I have a very strong interest in the intersections of chemistry and aesthetics and art, also contemporary art. So tonight I'm going to talk about the molecular elusive, which is kind of an elusive title, I guess, but really it's on time and aesthetics in chemistry. So I assume in this audience that a fair amount of you have taken chemistry in your life, and probably organic chemistry, and if you were a doctor, you either loved it or hated it. But hopefully this will make you love it again if you loved it before. So this is a quote from Claire Valence, and it says, "The huge variety of chemical species, types of reactions, and the accompanying potential energy surfaces involved means that the timescale over which chemical reactions occur covers many orders of magnitude." So what I'm really going to be focusing on in this talk is chemical species that exist for very, very short time frames, and the aesthetics associated with those, because chemists love those things. We're very excited about chemical species that exist for very short times. So just to give you a little refresher on chemistry, how many of you guys have taken chemistry? Like all of them, right? Yeah, okay. So you've learned some chemistry in your life, so you probably know some of this stuff. So there's all sorts of time frames associated with chemical reactions, right? So there's really slow reactions like rusting. This is actually an art piece by the performance artist Chris Burden, who died recently. And what he did was he had these steel beams up on a crane, and then he had a pad of cement that was 10 feet deep, and he dropped them one by one into a concrete pad. So that has nothing to do with my talk really, except for just showing rusting beams. And I'll talk a little bit about rusting, which is a very slow chemical reaction. And then there are also, as you know, extremely fast chemical reactions. So explosions are very fast. Combustion reactions are very fast chemical reactions. And this is just another artist who does stuff with explosions and fireworks and stuff like that. See, let this go. And then there are reactions that occur in between states, between very slow and very fast. Perhaps you saw this in your chemistry classes, the oscillating clock reaction. It's a little video of it that I'll show you. At first it looks pretty boring, but keep your eye on it for a moment, and you can see it just keeps shifting. So it's a complex iodine clock reaction. It's just shifting species to species over a time frame that we can watch pretty easily. So this is happening over seconds and minutes. Okay, so I'll move on from there. So just that gives you a feel. If I can figure out how to move on from there, let's see. There we go. All right, so various time frames that reactions occur over. And so when you think about a reaction, and probably many of you have done chemical reactions, at least in general chemistry in college, right? You have some starting material, it goes to some product, and you can see the starting material, you can see the product. But if you really think about it, in between those two material states that you can actually see are all sorts of invisible species that last for very short time frames. And that's really what I'm interested in this talk, is those species that you can't actually see, but despite the fact that you can't actually see them, there's still an aesthetics associated with them. So that's what I'm interested in. What I'm showing here is just the process, or sort of a shortened process for rusting going on. There's a little cartoon of it. And even in this process, it's going through a whole bunch of steps, but really all you see is iron to start and rusted iron at the end, even though there's all these species in between that exist for varying times, some of them very, very short. Okay, so this is your chemistry lesson. Just to remind you, you probably have many of you seen these type of diagrams before. They're called potential energy diagrams, and they're the way that chemists map reactions, or one way that chemists map reactions. So let me just remind you, probably many of you are having nightmares right now thinking about these reactions, SN1 and SN2. You might have learned them in your life. They're like the first reactions that you teach in organic chemistry. And what's being shown here, and I'm not going to go into every detail because it would bore you to death, is just that you have a starting material here, and it goes to a product over here. So that's really, it doesn't even matter what these things are, it's just starting from left and going to right, just to remind you. And what's being mapped is the energy associated with the process. That's what the curve is there. So the two species that I'm going to focus on this talk, transient species, are transition states. And just to remind you of what that is, it's basically on these diagrams, it's the high energy point, the top of the hill on the diagram. And then there's the intermediate. And the intermediate, as indicated on this left-hand diagram, is a little dip along the pathway. We call it a minima. It's still high energy, it's still very short-lived, but it's a little lower energy than a transition state. So the most important thing really on this slide is that transition states, species, things at the top of the hill, they last for 10 to the minus 15 seconds, or a femtosecond, about. Very short-lived species. And then intermediates are relatively longer-lived, 10 to the 10 to 10 to the minus 6 seconds, and we can actually track these and look at them, whereas these are just speculative things. They never really can be caught in any way. All right. So you're probably wondering, what does this have to do with aesthetics, this chemistry lesson? Well, what it has to do with is that, again, I'm interested in the aesthetics of these very short-lived species. And before I get to those, I just want to tell you there's a whole field of molecular aesthetics. There's about probably 10 people in the world who study it, including me, so it's not a big field. But most of the work within that field has been on stable, low energy, long time frame species. They're not these high energy things, but things that hang out that you can put in a bottle and study. And so buckyball is kind of a famous example of a molecule you guys have probably seen in ads and whatever, various places in your life. Right, so here's an example, nice pretty example. And it's been analyzed aesthetically by lots of different people, including myself. And so you could use all different frameworks of aesthetics to understand this. Platonic aesthetics, machine aesthetics, echoes aesthetics, etc. All different types of things. So I'll talk a bit more about what it means to study these in terms of aesthetics in a moment. But as I've said a few times now, I'm interested in the aesthetics in this particular work of really short-lived species. And so you're thinking, well, why would anybody think there's any aesthetics associated with them at all if you can't actually see them? And one of the reasons is because chemists, Polanyi and Zual, who are Stanford chemists, won the Nobel Prize for their work on this, said this about the transition state. So that's the thing that exists for 10 to the minus 15 seconds. Say the transition state is either one thing, namely chemical reagents, or the other, reaction products. Instead, it illustrates the mystical event of transubstantiation. So chemists use very strong language, aesthetically laden language, to think about these things or to describe them. We're very, very fascinated with them. We love them, even though we can't actually see them. Here's another quote from another Nobel Prize winning chemist, Donald Graham. He was at UCLA, about an intermediate. The intermediate that he's talking about here is this thing in the brackets. Okay, that's how we indicate an intermediate in chemistry, is with brackets. And so that's that high energy species that exists for about 10 to the minus 8 seconds. And as you can see, it's just a square with 2 lines. So it doesn't look that fancy, but it's called cyclobutadiene. And he says cyclobutadiene is the Mona Lisa of organic chemistry, its ability to elicit wonder, stimulate the imagination, and challenge interpretive instincts. And then he says more, but I won't forget. So you can see that these kinds of things elicit a lot of passion for chemists. We really love them, even though it just looks like a square. So, going back to the work by Zual and Polanyi, this is something that's underlying this idea of the aesthetics associated with these kind of species. And this is from when they won the Nobel Prize, what was written about their work, and it says that femtochemistry allows us in some way to get a different view, to see the movements of individual atoms as we imagine them. Then they are no longer invisible. So they created this technique that supposedly made us able to see transition states and intermediates, which is very, very cool. Okay, there we go. Okay, but what does it actually mean to see these things if we can't actually see molecules, right? And we really can't see super short-lived molecules. So this is a quote from a philosopher of chemistry named Joachim Schumer. I won't read it to you. But basically what he's saying is that it's not the liquid or the gas or whatever the thing is. It's the pictures that we draw of the molecules that are actually aesthetic. And that's the thing that we love, is the picture of the molecule, not the thing itself. Okay? That's a really, really important part of this. And that's true with the buckyball too. Buckyballs, we can't actually see the molecular form of a buckyball, we just postulate what it is, but then we think, oh, that's so beautiful, right? Okay, so to understand this, in terms of the transition state, this is from one of Polanyi and Zual's papers. And I'm just going to explain a little bit of it. Doesn't matter if you understand all the chemistry or not. What they're looking at to see this transition state is the reaction shown on the top. So it doesn't really matter if you understand all those symbols or not. Basically what they're doing is they're looking at a molecule where the two phi, is that phi? I don't even know. I don't know. Psi or phi, that little ring thing with the, whatever, okay, little Greek symbol, okay, where they're like this, and then they flip like this. That's the reaction going on. Okay, it's a cis-trans isomerization of Stilbe. So it's going like this, and in the brackets in between is when it is not like this or like this, but when it's like this or twisted, that's the transition state. So that's what they catch, what they're seeing. So let me talk about how they're seeing it, so you get the idea of what seeing actually means. What they do is they cause this reaction to occur with some light, and they capture it over a 300 nanosecond time scale, and they get a blip on a graph like that. Okay? And that's called a time snapshot. And then what they do is they take that and they map it onto a potential energy diagram like I showed you earlier in the talk, except for that this is a three-dimensional one. But same difference. And then what they do is they point at little places along the path, time zero, time final, right, like that, and then they have the intermediate, or the transition state there that they've drawn, okay? And that's what they mean by seeing it, is that they can map these pictures onto this diagram which maps to this. That's what seeing a transition state is. But that was like amazing. They won the Nobel Prize for doing that, okay? And chemists loved it. Okay, so you can kind of see all of that there. So that picture that they've drawn is the seeing. And really, this is the seeing, the blip here, and then the mapping onto a structure. Okay, go there. Oops, sorry, skip something. Okay, so again, why does that make it aesthetic? So It's a kind of complicated thing. I'm not going to go into all the details about it. I'll just say a few things to give you a feel for the kind of aesthetic analysis that I'm doing to understand these kinds of aesthetics. So one thing is that at the top, Stephen Weiniger, who's a philosopher of science, says transition state theory allows the chemists, in a sense, to visualize time itself, time that is completely tethered to space. So that's a little bit of an oblique philosophical statement. So you have to think about philosophy of time, which isn't that easy, but I'll give you a little bit of feeling for it, okay? So one thing is that when we draw these structures of what we imagine these transient species to be, then we symbolically concentrate all this information into the structure, and that has an aesthetic quality. So, as I say here, static structures of transition states and intermediates, like cyclobutadiene, which is just this square, compress time, space, and energy into one single visual structure, and that has a lot of meaning aesthetically for a chemist. That's one aspect of it. Another thing is that when we have static pictures of really short-lived things, there's actually a narrative embedded in those really short-lived species in the structures. I said that sort of weirdly, but I think you get the idea. So this is a famous picture by Harold Edgerton, and you maybe have seen before, and he did a lot of stop-action photography, one of the first people to do it at MIT. And he had this picture of a bullet going through an apple, and all of you looking at this, you can imagine the whole sequence of events that's going on when this picture was taken. You can imagine somebody shooting the gun, you can imagine the bullet traveling, you can imagine it going through the apple and coming out the other side, and at some point, the picture was taken. And so it's the being able to trap that image, right, within the narrative that goes on that is aesthetically interesting to us. I won't, again, read this whole quote because it's kind of long, from a philosopher of photography, actually, but says what static images are capable of depicting are something called specious instance, which are parts of larger movement represented by the image. Images can thus represent a movement by depicting perceptually minimum parts of it. So again, that's kind of a mouthful. I barely got it out myself. Okay, but I'll try and summarize for you what the aesthetics associated with that is. So basically, if you think about it, instants have no duration, right? Every instant is passing. There's no duration associated with it. So therefore, the instants are actually imperceptible. So he creates this category called specious instance, which is the smallest perceivable part of an instant. So that's what he's talking about there. So what I'm saying is that time frames of transition states and intermediates are specious instants, because we can know that they're a femtosecond or a millisecond or whatever. So we can perceive them in some way, at least spectroscopically, and that it's depictions of transition states and intermediates express the imperceptibility of time, and really that's the thing about them that is aesthetic. They allow us to get a grip on time, or the imperceptibility of time, I would say. Okay, so the very last thing, I thought you would like to see if I can make this work. Let's see. It's Chris Burden's piece, just because it's fun to watch. So here's the steel beams. I'll just show it for a moment as he drops one of them into the cement. There you go. And it just drops lots and lots of them. I wouldn't want to be standing under there. Okay, thank you.